All right, so for today's notes, we are going to be doing limits graphically. As I'm doing notes, since there's like 21 of you in the class, if you have questions, you're more than welcome to type it into the chat. I do have that open in front of me. Or you can just unmute your microphone, give it a second, and then just kind of yell at me the question. That also goes if I happen to go too fast, because again, I can't really see how much you've written down when you're not in front of me. But today we are going to be looking at limits graphically. We'll be looking at limits 3 different ways. Obviously, we'll talk about what a limit is, and then we'll be looking at limits graphically, limits analytically, which is another way of saying algebraically, and then limits intuitively. So the first thing I did want to do is define what a limit is, what the notation is, and kind of how we can think about it and what it represents. So the first is the notation that I want to use for limits. So we will write limit, we'll abbreviate it as LIM. You see like this subscript underneath it with X, that can be another variable, but if we're talking about f of X, we are going to use X. An arrow and a number, then we have f of X and equal a value. If I want to change that symbol into a sentence, basically when I see that, what's typed up on the screen, I read that as the limit as X approaches 4 of f of X is 3. So some different things that I want to make sure we notice that when we're talking about the limit. This arrow that we see in the limit is translated as the word up to approaches. So we don't care if the graph is not exactly at that value. We're talking about what is approaching. And when we say approaches, we're going to call this from both directions. It means, so if you're looking at that, I do have just kind of 2 blank graphs right now. I'm going to draw 2 separate graphs that will both have a limit as X goes to 4 being equal to 3. So one graph I might draw, I'm just going to draw a basic quadratic. And this will be an example of a graph where the limit as X approaches 4 is equal to 3. Why is this true? So here's X is equal to 4. I'm going to put a die line there just for the reference. The limit is, so as you're on the graph, as your X values get closer and closer to 4 on both sides, the Y value that it is approaching is 3. So notice that, in fact, it is 3 here, like f of 4 is 3, but the limit is only concerned about what it is approaching. For example, this graph would also have a limit as X approaches 4 is equal to 3. If I just draw a straight line and I put a hole there, this one would also have a limit as X approaches 4 is equal to 3. So again, we're looking as X gets closer and closer to 4, looking on the left and the right hand side, we can see that the graph is getting closer and closer to the Y value of 3. Is it equal to 3 exactly? No, there's a hole there, but the limit is just concerned about what it is approaching on both sides. Questions so far? All right. So we have different types of infinities. That first example was where the limit was approaching a numerical value. We had X was approaching 4. We can also look at examples where the limit can approach infinity or negative infinity. So this first one will be read as the limit as X approaches infinity of f of X, and then the second one, the limit as X approaches negative infinity. And when you're doing limits at infinity, you're looking at the extreme left and right hand side of the graph. Obviously, the left hand side will be towards negative infinity, and the right hand side is towards positive infinity. So again, a limit is talking about what you are approaching. So when you're looking at this graph, when I have the limit as X is approaching positive infinity, what does it appear the graph is approaching? And the answer to a limit is the y value. So we can think about it as x goes to infinity, your y values are approaching what? Anyone want to take a stab at that one?
-2.
-2. Oftentimes when we think about limits at infinity, those are going to be associated with end behavior. In fact, whenever you talked about end behavior before, you're actually doing a limit. And so oftentimes, since it's end behavior, they are directly attached to horizontal asymptotes if they exist. Looking at this other example, if I have the limit as x goes to -infinity of f of x, what do you think our answer is going to be for the limit as x goes to -infinity of f of x?
Infinity.
Infinity. So one option, your answer could be infinity. Another option is infinity is not really a number, so we will also consider that as an example of where the limit is d in e for does not exist. Both of those answers are okay with me. Like if you said the limit was infinity, that's fine. Or if you said d in e, that is also fine. Notice I would not say equals infinity. An equal sign implies that it is exactly equal to that, and infinity is not really a number, so we'll just say the limit is d and e, or the limit is positive infinity. But either of those answers would be okay. So we have limits approaching a number, we have limits approaching infinity, and kind of the last vocab word we'll use for limits, then we'll look at some different types of examples, will be what we call one-sided limits. So one-sided limits are exactly kind of what they sound like. They are limits where you're only looking at one side of the graph. So I have a piecewise function here, and if I'm looking at these one-sided limits, you'll notice that first at the top there's one with like a little negative sign written in the exponent, another one that has a little plus sign written in the exponent, and then the one towards the bottom right-hand side is just the regular limit. Whenever you see a plus or minus in the exponent, it tells you that you're only looking from one side. So this first one where I have the limit as x goes to 1 and you see the negative there, we're going to interpret that as the limit as x approaches 1 from the left. If we think about a number line, the negatives are on like the left-hand side of the number line, so a little minus there is going to be coming in from the left-hand side, what y value is the graph approaching. Likewise, when we see the plus sign, that is going to tell you that you're coming into 1 from the right-hand side. Whenever you don't see a plus or a minus, you will always have to consider it from both sides. So looking at this one, feel free to unmute your mic and kind of shout an answer, type it in the chat if you feel comfortable. If the limit of this graph is approaching 1 from the left, what will we say that limit is equal to? Any guesses?
2.
2, yes. So coming in from the left-hand side, as x gets closer and closer to 1, the graph is approaching 2. Notice there's a hole there, but that doesn't matter with limits because we're talking about what is it approaching. So likewise, if I'm looking at the limit as x goes to 1 from the right-hand side, what are we going to say the limit from the right-hand side is equal to?
-1.
-1, easy enough. Coming in from the right-hand side, it's -1. And then you can probably see where this is headed. If I just want to know what the limit is approaching as x goes to 1, so we have to consider the left and the right. I notice on the left-hand side it's going to 2, but on the right-hand side it's going to -1. So what do you think the limit as x goes to 1 from both sides is going to be equal to?
Both
The answer is does not exist.
Oh.
And I know we've all seen Mean Girls, and there's that scene at the end where it says the limit does not exist. So this will be one of the cases where the limit would not exist. So that's going to bring us to kind of the last definition we're going to look at today before I just kind of show you a bunch of examples. So we have limits approaching a number, we have infinite limits approaching infinity, one-sided limits, and then we have this concept. A two-sided limit exists if and only if. So two-sided is going to be one where we don't have the plus or the minus. And a limit is only going to exist if the limit as x approaches the number from the left of f of x is equal to the limit as x approaches c from the right of f of x. So if the left does not equal the right, then the limit is not going to exist from either direction. So we do have some common does not exist situations. The first and the most obvious one is if you have some value c, is if you just have a piecewise function. Open or closed circles don't matter. But that would be a clear, obvious situation where the left-hand side does not equal the right-hand side. You could also have an example where maybe one side approached a vertical asymptote and the other side was another function, whether open or closed. That's another clear example where the left-hand side does not equal the right-hand side. Or they could both be asymptotes, and then those are clearly going in opposite directions. So those will be three examples where the limit does not exist at C. To be clear, there are limits everywhere else in the graph because you could pick any other x value and the left and the right-hand side would match. It's just at the issue when the left and the right-hand sides don't match up.
Mr. Brown.
Yes.
Would a parabola be a two-sided limit or no?
A parabola, so I'm going to do a different color. If you just have this is your function f of x, then this one, the limit will exist always. For x going to a value, so I won't talk about as it goes to like positive or negative infinity. And that's because any point you pick on a parabola, as you come in from the left-hand side and the right-hand side, you're going to the same value. So some people think about it this way: if your function is basically continuous, then every limit as x goes to c is going to exist.
Okay.
Any other questions? All right. I added this slide. I think it's clear, but sometimes it's not, so I just wanted to make sure it was clear. Up until this point, we have pretty much only talked about the values of a function. So like when I say find f of 3, f of 4, that is talking about the value of a function. It is talking about where is the function. So it's asking you like at f of 2, where is that function? The limit, on the other hand, is asking you what is the function approaching. And I want to make sure we can kind of distinguish between the two. So like if I'm looking at this graph, this is a linear function. There's a hole at x equals 2 and then a point defined. We have the value of the function. The value of the function is 3. That is where the actual function is located at. The limit of the function, again, we do have to always check the left and the right, so we don't see a plus or a minus there, so we do have to consider it from both sides. The limit cares about what is it approaching from the left and the right, and so the limit of this function is equal to 1. So in this case, the value is not equal to the limit. That's the only location on this graph where that's the case. For example, if you pick any other random point, the value and the limit would be the same because you don't have really any continuity issues. Like if I picked, we'll just say -3, we can state the statement that the value at 3 is equal to the limit at 3. And that's true for pretty much all continuous functions. The value will be equal to the limit. Questions? All right.
Actually, Mr. Brown,
Yeah.
so the limit is just like a certain point on the graph. It's not like an actual point where the graph just stops, like an actual like limit per se.
So when you say actual limit, you have to think we're talking about limits in the math terminology.
Yeah.
And so like when I'm talking like in this piecewise, the limit as x approaches 2 is 1. Because as you get, you can think of it as you get infinitely close to the x value of 2, the y values get infinitely close to the y value of 1. If that makes sense.
Yeah.
Any other questions? All right, so the last part of my notes, I don't have any numbers. I just have some like random shapes of graphs. Some of it's going to repeat what I said, but I just want to kind of summarize, like if you see this shape in a graph, this is how we can interpret the limit. And then pretty much I'll wrap up today's notes. Tomorrow's notes will be more algebra based. Today's notes are definitely very visual. So the first question I ask, graphs we know can have closed holes and open holes, depending on if the function exists there or doesn't exist there. If you're talking about the value at a particular point, so I'm just going to call the location we're talking about the x value of c. For the first one, if it's closed, we know that the value does exist and the limit also exists. For the second one, we have the open hole. There are no points defined anywhere else. So we will say f of c is undefined. You might be asking why we don't use the word does not exist. We tend to, just by convention, use does not exist for limits. So we'll say that the value is undefined. The limit, does the fact that this is an open circle affect whether the limit exists or not?
No.
No. So f of x still exists because, again, we can still approach the same value from the left-hand side and the right-hand side. F of c would exist if, say, there was a closed hole above it. Other types of graphs that we'll notice. Jumps, we'll just kind of talk about this one in general. For either of these graphs, we know we can talk about the limit as x approaches c from the left. We can talk about it as x approaches c from the right. And I can talk about the limit as x goes to c overall. And when I'm saying c, we're just going to pretend that this is the x value of c. So the green one, does it have a limit coming in from the left-hand side? Yes or no?
Yes.
Yes. Circle doesn't matter. So likewise, coming in from the right, it also has. Would the limit overall exist?
No.
No. The left and the right don't match up. The other one is basically the same, and just kind of to be extra clear, yes, we have a closed circle, but that doesn't affect the left or the right-hand limit. Some students mess up, and even with it closed, they want to say the limit exists. They're like, hey, it exists there. But when we're looking at x goes to c, we have to consider both sides. So it would not exist. I might also talk about just the value This first one does not have a value. The purple one does have a value because it does have a closed mark on that C. Questions there?
So if there was two closed circles, would it be? Would you?
If it's two closed circles, you would like there would still be a left limit, a right limit, and no limit overall. But technically, we have two closed circle. This would not be a function because it fails the vertical line test. And so in calculus, when we talk about limits, we're mainly going to stick to actual functions. So this one, since you have more than one y for each x, we would technically just say that that's not a function. Any other questions? All right. Then we have asymptotes. Looking at these three graphs, so these are just kind of three different types of vertical asymptotes I have. We'll just call them 1, 2, and 3 going from left to right. Do any of those three have a limit when you're considering it from both sides? So like if I just say the limit as x goes to c, would any of them have a regular two-sided limit?
The middle one?
The middle one, so you could argue, so the limit as x goes to c of this graph, where would we say this limit is headed as x goes to c?
Infinity.
Infinity. But infinity, remember, is just another case of D and E. So like you could argue that the limit is infinity, but officially the limit's going to not exist because it is increasing without bound at that vertical asymptote.
Okay.
Would any of those graphs have a one-sided limit that exists?
The right one.
The right one, and which limit is existing for that one?
The one that's like to the positive one.
To the positive. So from the right, f of x would exist. Do any of those have a value that would exist just at the asymptote? No, I didn't put any closed circles on there. Some things I will talk about notation, especially because this is an AP exam that will have some free response questions. They're very picky about notation. So when you write a limit, you never want to have just like the limit as x approaches like 3. That's kind of like having a square root sign with nothing underneath it. So you need to have the function after it. So if you don't know what the function is, you definitely want to make sure you label it as f of x to make sure that you're doing complete notation. Last slide I have, so that was mainly vertical asymptotes. Here are 3 that have some horizontal asymptotes and just some different shapes you can see. I have an exponential one, I have a sine or cosine graph, and then I have a dampening oscillating function. And we're going to talk about the limits as x goes to negative infinity of these graphs and the limit as x goes to positive infinity of these graphs. And we'll just kind of talk about whether it exists or doesn't exist. So that first one, that first graph, that exponential, what would we say the limit of that graph is as x goes towards negative infinity?
Under like D and F.
So yeah, so you can say D and E, or you can say it's approaching positive infinity since it is going up as you move backwards. Would you say, we'll just say whether it exists or doesn't exist, would we say the limit as x goes to infinity exists or doesn't exist?
It would exist.
It would exist. So it does exist. It would probably help if I have some numbers here. So we're existing it, and we know it exists because we see a horizontal asymptote. It may never reach that horizontal asymptote, but it is approaching it. So whatever number that horizontal asymptote is what the limit would be equal to. The trig function we know is periodic. It repeats that shape pretty much forever. Is the trig function ever going to settle down and approach a certain value?
No.
No, like it goes up to, like if it's regular sign, it is bound between -1 and 1, but it's basically always going up and down, up and down. So the limit at positive infinity and negative infinity will be d and e. The exact reason we would say in calculus terms is that it's oscillating, but d and e is fine. This next one is a dampening function. So one side looks like trig, but then it kind of gets smaller and smaller and smaller and smaller. So let's talk about going to negative infinity. If you're moving backwards, I see that it is getting wider and wider. So we can say that the limit does not exist. As we move the other direction, going towards positive infinity, we notice that it gets kind of like smaller and smaller and smaller. So there is some sort of horizontal asymptote there. So it does exist as you're going to positive infinity. Even though it's oscillating, you can kind of see there is some sort of horizontal asymptote going on. Even though it is crossing it, it does seem to be leveling off at that value. Questions or concerns?
So for the dampening oscillating function, as you go towards infinity, it will eventually get close enough to the asymptote that it looks like a straight line.
Yes. The example of that function is something like, well, this won't be exactly like it, but it's related to a series that's something like 100 times -1/2 to the x value. So basically it's like you keep multiplying a number by -1/2, so that's why it's switching between positive and negatives. And if you keep multiplying by numbers by -1/2, they get smaller and smaller and smaller, closer to 0, while alternating plus minus, plus minus, plus minus. So eventually it will get really, really close to 0. And so that's why we'll say that it exists, because it is approaching a number. Any other questions?
Can the horizontal asymptote only be 0 for the third one?
It depends on what it is. It's probably 0, but like if I drew, like I can draw one that settles like this. And say this is the line y = 4. Then we would say the limit as x goes to infinity is 4, since that's what it's leveling off at. So it depends on where it's leveling off at and what the function looks like. The main thing I think about it is when I'm dealing with limits at infinity, I look for some sort of like horizontal asymptote or horizontal trend. Any other questions? All right, so I'm going to finish today's notes there. Here's a checklist. Again, I do have this lesson recorded. It takes a while to process, but it will show up in about 20 or so minutes is how long it's been taking. So join my remind if you haven't already. There's still a few of you who haven't. Please, if you haven't yet already, also sign up for my AP Classroom, making sure you hit turn in when you complete that task. Continue working on homework 0, which is the prereqs. Again, that's due Friday. If you need any help with prereqs, you can come see me during office hours. And then you can also begin working on homework number 1. It's limits graphically. It shouldn't take you too long to do, but remember, I'm only checking homework, same as last year, like on quiz day and test day, so you don't have to worry about getting homework 1 done until the 26th if you're feeling a little bit overloaded right now. So at this point, I'm going to...
Where's the code for the AP Classroom?
It is it's different for each period, but I have it typed into the comments of the assignment. I don't have it memorized. But if you go into the assignment, you'll be able to see it.